concerned, if you don't or if you don't turn up for the quiz, and today we could possibly have one, right? We could possibly have one. So listen well. This lecture is going to be hard, to be honest, if you're not listening. I'm telling you the truth. If you're not listening, this lecture is going to be extremely hard, right? Even those who are listening, it's still going to be hard. Okay, I'm not trying to scare you, but in fact, I am trying to scare you, right? Okay, so just listen, right? Just listen to the presentation. It's not going to be simple. It's not going to be it's not going to be easy if you're not listening. So just we're going to look into lectures, and then as for the if you check on your book, right, for the momentum, you'll see a lot of equations there. You'll see a lot of equations. But what I want out of the equation is not for you to memorize, but for you how to know how to use the equation. Okay, that's the bit that I want you guys to know, right? How to use the equation exactly. All right, so that is it. And without further ado, we shall proceed with the final lecture, with the final chapter of fluid mechanics for fluid mechanics 1. Right. Okay, so we are doing chapter 6, which is momentum analysis of fluid flow. All right, or momentum analysis of fluid flow systems. Okay, listen well. This chapter is going to be challenging, very challenging. Okay, right. Okay, as for the objective of today's lecture, to identify various kinds of forces. Okay, just forces, yeah, and moments acting on a control volume. I think moments, we're not going to do this bit, right? We're not going to do moments, we're not going to do inertia. I think just the forces acting on control volume, right? Okay, I'll fix this. Okay, you don't have to worry. Right, we're going to be studying about the various kind of forces acting on control volume, just the force acting on control volume to be exact, right? And then we shall use the control volume analysis to determine forces acting or associated with the fluid flow. Okay, this simple, right? This simple. We shall identify the forces on the control volume, and then we use control volume to determine the forces acting for the flowing fluid. All right, so that's it. Right, so these are some explanations, some theoretical stuff. It's not going to come out in the test, to be honest, right? But I would rather you understand what they mean. Okay, Newton's law, relations between motion of bodies and forces acting on them, right? Okay, Newton's law is talking about the motion of bodies and forces acting on them. You have body and you have forces acting on them, right? It's that simple. Newton's first law is stating that, okay, a body at rest will remain at rest, and a body in motion will remain in motion, okay, at the same velocity in a straight path when the net force acting on it is zero. What it meant is actually when you have a body, I have not. Okay, just give me a sec. Yeah, I need to draw something. I need to work on this. Open up. Since opening the whiteboard. Right. Let's get back to where we were. Right, okay, a body at rest remains at rest, and a body in motion will always be in motion at the same velocity in a straight path when the net force acting on it is zero. Okay, when the net force acting on it is zero. Now, what does it mean by this statement is that, all right, what it meant, okay, by that statement is that when you have a body, okay, when you have a body, okay, let's assume you have a body, okay, a triangular. When you have a body, this body will never move. Okay, when it is resting, okay, it is always be in this position, exact position, without interference of any force. Okay, without interference of any force. If all these forces acting on it, zero, F, everything is zero. So this 0, 0, 0, 0, it will be always at rest. Okay, the same goes when you have body. Okay, when you have body, that is currently moving. Okay, we're going to be talking about vector in this study, right? I know it sounds okay. Just follow along. Okay, you have a body that is currently moving. Okay, it's moving in this direction. It's currently moving in this direction. Now, assuming that you don't have any forces acting on it, you don't have any force going this direction, this direction, this direction, this direction, or this direction, this body, right? This body will keep on moving. Will keep on moving. Okay, so that's basically what it says by the um, first Newton law. Okay, this is what it says, right? Body at rest will remain at rest if all the forces acting on it is zero, right? It just stay there. But if it moves, right, without interference of force, gravity, anything, right? So it'll just move continuously without stop, right? So that is what being said by the first Newton law. Okay, so that's it. Okay, it is as simple, but sometimes it's quite hard to understand. If you don't have force in it, force it means gravity and stuff and so on. Okay, friction force and so on and so forth. If you don't have anything, it will always move. Okay, remember that. Okay, so a body tends to preserve its state of inertia. Okay, the state of the initial state. Okay, that's it. Right, the Newton's second law. Okay, Newton's second law. The acceleration of a body is proportional to its net force acting on it, and it's inversely proportional to its mass. Right. Okay. If you read this, okay, kalau you lapar kan, you baca this statement, okay, it's not gonna go it's not gonna go in. You can't digest it easily. Rather, okay, I'll show you. It says that acceleration of the body is proportional to the net force acting on it. Right. What it means is actually, okay, acceleration of a body, you have F equals to ma. You know why they have this arrow, right? This arrow, okay, this arrow at the top of F, meaning it has direction. Has direction. Okay, direction. Okay, it has direction. We'll be playing with this lots and lots of them in this chapter. Okay, it has direction, yeah, right? Mass, no, mass is right. Okay, we're gonna be talking about A here, right? This statement says acceleration of a body. Acceleration of a body. Okay, if you were to rewrite this, so it becomes acceleration of a body equals to F, okay, divided by m, right? Okay, so acceleration of a body is proportional to its net force. It's proportional, okay, is directly proportional, and then inversely proportional to the mass. So it's actually explaining the words. Okay, it's actually explaining this equation, right? Simple, simple stuff. They just all right. Okay, it's actually very simple. Okay, the Newton third law. Newton third law says that when a body exerts a force on a second body, the second body exerts an equal opposite. Okay, when a body exerts a force on a second body, the second body exerts an equal opposite force on first. All right. Okay. Actually, this statement here is applicable when you have steady flow devices. Okay, steady flow devices. Right? This Newton third law is actually applicable in such a way that, okay, if you have an open system, you have mass in, you have m in, okay, and then you have mass out. You have mass in, and then you have mass out. You know, when you have this when you have this flow, you'll have momentum. The moment you have m and the moment you have v, the velocity of the fluid, okay, the moment you have v1, vn, and then v out, okay, the moment you have m, you have v, you have momentum. Okay, this is clearly the definition of momentum, right? Momentum is actually the product of these two, right? Simple. The product of these two, momentum, right? The moment you have m, you have v, you have momentum. Now, it says that when a body exerts a force on a second body, okay, let's just assume this one is a body. Okay, this one is the first body, this one is the second body. Is the applicability. I know it's talking about two bodies, right? It's talking about two body, but I would bring you to the attention of steady flow devices. Steady flow devices. Okay, steady flow devices. Now, in this direction, you have momentum going this way, right? You have momentum going this way, okay? And then it's going this way, right? Okay, and then you have flow out, you have momentum going in this direction. Okay, we have momentum going in this direction. If this is the case, right, you'll have the same amount of momentum going this direction and this direction, right? And then this device, well, actually the applicability later on is in the calculation. Okay, it's hard for me to explain to you now, but when we do the stuff, the calculation later on, you will be able to see. Because when you have force acting in this direction, there will be another force acting that is to fight along, right? To fight along in the opposite direction, right? When you have something coming momentum in this way, you'll have another momentum, right, acting on this way as well. So you have, if you have momentum in this way, you will have another momentum coming in this way, right? To support the two momentum. That is what being said by the third Newton's third law, right? When a body exert force on the second body exert an equal and opposite force on the first. So it's like, okay, when you have forces acting on the right, you have forces acting on the left, okay? And they will be balanced, right? And this will influence something in the calculation later on, which we shall see, right? Shall see. Very interesting. Okay, Newton's law. Why do you think they're giving you this? Because all of its applicability will be shown in the calculation later on. Okay, just remember that. From the Newton's second law, is giving you this: F equals to ma. F equals to ma. Right? Why do you have direction? Why do you have arrow? Okay, at the top of the F and A, is actually, it gives you direction, right? When you expand the A, okay, A is actually V, the velocity divided by time. Okay, when you expand this, and you can even like regroup this, momentum is the product of mv. So momentum can also be said as the product of momentum, the rate of change, of momentum. Okay, the equation, I think, is explained here. Linear momentum is just momentum of the body, is the product of mass and the velocity. That's it. Whenever you have mass, when you have velocity, so you have momentum of the body. Linear momentum, or just the momentum of the body, product of mass and velocity. Mass multiplied velocity, you have the momentum. Newton's second law is usually referred to as linear momentum equation. So if you want to know what linear momentum equation is, this is linear momentum equation. The momentum of a system remains constant when the net force acting is zero. Okay, again, we go back here, right? We go back here. We go back right here, right? Okay, we go back to this drawing. Okay, it says that momentum is what it says here. Okay, the momentum system remains constant. Okay, when you have it flows, okay, momentum is only there. Right, when this thing is flowing, it has mass, it has velocity, so you have momentum. Right, when you have this thing moving, right, so without any force acting on it, so it will just momentum will be constant. Right, the momentum of a system will remain constant if there's no net force acting on it is zero. When the force acting on it is zero, so that's it. Right, so when you have a movement, when you have mass, when you have mass in here, when you have velocity when it moves, you will have momentum. All right, okay, so when this F, all the F acting on it is zero, so you have momentum is constant, it will never change. Okay, it will never change. I know it sounds a little bit, for those who are not familiar with this, it's gonna sound very very hard. Okay, but then again, I think we'll get a clearer view when we do exercises later on. And this chapter, the reason why I put this one towards the end is actually because this one would require the knowledge of all the previous lecture, especially your Bernoulli equation, right? Especially the Bernoulli equation, right? I think you have to recall. I think I'll help you in recalling the Bernoulli equation. Okay, so you don't worry about this, right? You don't worry about this. So you have F equals to MA, so you expand the MA. Okay, I think this is quite straightforward. So move on to the next one, okay, which is one of the most important part of this lecture, that is to choose a control volume. When you'd like to analyze a fluid flow system, you have to choose the control volume. Okay, you have to choose the control volume. We have three types of control volume. We have fixed. Okay, you have fixed control volume. What does it mean by control volume? It's a volume of study. I always tell this to my student. What does it mean by control volume? Is the volume of study. You are studying the 3D situation of this area. Okay, this area is the area of study. Okay, is the volume of study. So it is called a control volume. We have three types of control volume. We have fixed control volume. We have movable control volume, and then we have deforming. Okay, deforming control volume. Now, what does it mean by all this? Fixed control volume, we have something fixed, okay, like this one here. Okay, it has a tripod, okay, supporting the water flow. Okay, so it can't move. So you the best that you could do is to analyze it, okay, in its just direction. Okay, the control volume will never change. Unlike a plane, okay, a plane, when you have a situation such as plane, why does it say that it is moving? Why? Because for a plane, if you have a plane, okay, if you have a plane that is okay, if you have a plane that's moving, okay, you have the control volume here, right? We have the control volume here. This is your CV. Okay, this is your CV. Okay, fine. This is the study area. However, you have to know that this plane is moving. It's not going to stay here forever. Okay, it'll move in this direction. Okay, assuming it's moving in this direction. So your control volume must follow along. This control volume here, it must follow along, all right? The plane, the moving plane, right? This plane is moving, right? You have to move along together with the plane. Okay, it must move along together with the plane. However, the control volume itself does not change. This is what we call by movable control volume. All right. And this one is, I think, is self-explanatory. For the piston cylinder device, you have a control volume in here. If you are choosing this as a control volume, the control volume in here, it changes. Okay, it deforms. Okay, I think it goes big, it goes small. Okay, when this piston is going down, it's increasing in size. The control volume is increasing in size, and the moment this piston goes up, it is decreasing in size. Okay, decreasing in volume, right? That's what we call this one as deforming or changing. Or deforming, I think it's yeah, it's deforming control volume, right? Okay, this one's fixed. This one's fixed. This one is changing. Okay, this one is deforming. Okay, so these are the types of control volume. Okay, and then okay, I think we're done with control volume, and now the forces acting control volume. We have to finish all the lecture first before we try some exercises, right? Only after finishing the lecture, then we can proceed with the calculations. I think I'm not going to explain the equation much because I know you won't memorize anyway, right? Okay, I would rather show you how to use the equation. Okay, I would rather show you how to use the equation, right? Okay, let's just choose this. You have a body, right? You have a body, and then you have a control volume in it. Okay, when we talk about forces acting on a control volume, okay, this is your control volume, right? Okay, I think we just choose the control volume. This is the chosen control volume. This is the chosen control volume. This is the chosen control volume. Now, in order to study the forces acting on the control volume, this is the control volume. You need to know about the forces acting on it, right? Okay, so the forces acting on the volume consist of, there are two forces. One is the body forces. Second is the surface forces. Okay, you have the control volume. One is the body forces, okay, namely gravity. That is one example of body forces, right? Body forces, the gravity. So that's why the force acting on a control volume equals to F of the body, and then F forces on the surfaces, right? The surface of the control volume. This is where it gets challenging, to be honest. This is where it gets challenging because I think you need to go back to your static, right? You still remember the components of static, like the force acting, and then you have to find the components of the force in the x direction, in the y direction, right? But this one is 3D. Okay, you have to find forces acting on the x, on the y, on the z direction. Okay, so that is basically why it's making it a little bit hard to understand. Okay, this chapter is one of the chapters which is very hard to understand, okay, in fluid mechanics. So if you're following me, that's good. You don't need to worry about this. Don't worry about the equation, okay? I'll be showing you lots and lots of equations, so don't worry. We're going to be looking at them when we try the exercises later on. We're not going to be using most of them. We're not going to be using like most of the equations that are being shown. Rather, we use the specific ones, okay, towards the end of this lecture. So just bear with me for a bit. Okay, bear with me. I'm gonna be explaining to you. Okay, we walk through it together, and then we'll try some exercises. Don't worry, we're gonna be trying lots of exercises on this. In fact, I'm gonna give you one exercise for you to know, for you to do, and then we shall discuss the answer out. Right? Don't have to worry. Total force acting on body. Okay, the total force acting on us as control volume is the force acting on a body and the force acting on a surface. Okay, that's it. All right, force acting on the body, force acting on the surface. Okay, the rest you don't need to know. Okay, most common body force is gravity. I think that is the only thing considered in the book. That is the only thing considered in the book. So if we were to talk about the force acting on the body, is just the gravity, right? It's just the gravity. Okay, most common it says body force is gravity, which exerts a downward force. Okay, it pulls the body downwards. All right, push the body downwards. In every differential element is just the body itself. Okay, of a control volume. Gravitational force acting on the fluid element. Okay, this is the equation of the gravity. Okay, don't worry. The gravitational vector in Cartesian, okay, coordinates. Right, okay. If you study the Cartesian coordinate, you'll have this, okay, the z, y, x, okay, x, y, z, okay, that's common. Again, we can put them in the vector format, right? A vector means direction, all right, whether it's going upwards, whether it's going downwards, whether it's going the right hand side, the left hand side, and so on. I think we need to specify them, the direction of movement, right? The direction of movement, or the direction of the force, to be exact. The total forces acting on the control volume, okay, the body, and then this is the I would say the gravity, isn't it? Okay, this is the control volume. Okay, acting on the control volume, because you have two, right? You have the force, the total body force is made up of the control volume, okay, the body, and as well as the surface. Okay, this is the body, this is surface, right? So rho multiplied with v, here you have m, right? Rho multiplied with v, which is the volume, right? You have m cv and the gravity. Okay, so surface forces are not as simple as to analyze, because okay, normal stresses, you have normal stresses. Okay, surface forces, this is one of the surface, yeah, in a control volume, okay, for the body. The surface, okay, you have normal surface, you have shear stresses. I think okay, we'll discuss more on this. All right, let me just show you this. Okay, let me just show you this. Okay, it looks ridiculous, to be honest. Okay, just this is the surface. Let me talk about body here. We have a body, and this is the force of the body. Okay, we just talk about this bit here. When you talk about this, okay, this is the body and this is the force of the body, right? When we talk about surface, if you want to talk about surface, F on the surface, F on the surface is a little bit hard, because you have to consider normal stress, you have to consider about shear stress. Okay, this is it. When we talk about surface, yeah, this is control surface. So control surface here, let's just assume that you have okay, you have force. Okay, you have force acting on the surface here, and this one you just shift a little bit, okay, from A to B. Okay, let's have a look. Let's analyze this. You have a surface, you have a force. You have surface, you have force. This one here, you just turn slightly a little bit. Okay, have a look at the components in X direction, the components in Y direction. See, X and Y. I think this one is self-explanatory. I think you understand this. If you need to know about the X force in the X direction, you use F cos theta. If you need to know the F acting and in the Y direction, you use the F sine theta. I think you learned this in static, right? It's quite simple. Okay, so this is quite simple. However, the moment you change this, can you have a look at the magnitude, right? It's changing. We still have the same F. However, if you turn a little bit, try to have a look at the F's X in the X direction. See, it's different now. Okay, this one is in the Y direction. It's different. Okay, it's different. So that's why in the study of the forces, is a little bit hard on the surface. Okay, if you're standing surface, and furthermore, this is just 2 dimension. Yeah, the x, y, you still have another dimension, which is the z. Okay, this is just 2 dimension here, only 2 dimensions shown. You have the x, you have the y. You still have another direction actually of the if we were to study about the Cartesian coordinate. Okay, you have the x, y, z. Okay, so if you were to put to put them back into this equation, so we study about the body. This is the force of the body. Okay, and this is okay, the surface. Okay, if you study about this, the surface force is given by this. Okay, is given by the differential surface. Okay, you have this. This depends on the normal stress, shear stress, and so on. So you have all this, right? So you have the force is equal to the force of the body here, and then force of the surface here, right? So if you were to rewrite this, so the total force of the body, okay, is the one for the gravity, okay, and then this one for the surface, for the pressure, viscous, and other. All right, this is the total force. Okay, but still you don't have to remember. Okay, you just need to know this, right? I'm not asking you to remember all these equations. We would rather show you, right? Okay, so don't worry when I told you don't have to remember. Okay, so this is how it looks like. Okay, the component stress. Okay, Cartesian coordinates on the right top and front surface. When we talk about, okay, this is the what do you call the unit? Okay, the what do you call that, the component. Okay, let's assume that this is the component. When we talk about surface, okay, you have to consider about surface. If this is the surface that we're talking about, so this will be your, okay, you can define, you need to know them in the x, okay, in the x, in the y, in the z direction. Okay, you need to know this. If we're talking about this surface, so this is x, this is z, this is y direction. Entirely up to choose. Anyway, entirely up to you. So you have to know where's the x, where's the z, where's the y. Okay, if x is here, y is here, so be it. All right. So you just follow accordingly. Okay. Don't worry. Okay, don't worry. All right. Okay. Just few more minutes until we try out some exercises. Common simplification on the Newton's law is to subtract the atmospheric pressure and work with gauge pressure. Okay, I think during the big I think Miss Ain taught you about the pressure, I suppose. I really hope that she taught you about the pressure, the difference between atmospheric pressure and the gauge pressure, right? The gauge pressure is actually the one that you measure. Okay, the one that you measure on top of atmospheric pressure. Okay, allow me to just share with you. Just talk a little bit about pressure. Okay, we have absolute. We have absolute vacuum. This is what we call by 0 Pascal. Okay, assume this one is 0 Pascal. And then, okay, 0 Pascal, right? And then when you measure the temperature, this is 0, right? Okay, when you measure, when the pressure increases, when the pressure increases until it reaches 1 or 1,325 Pascal, this is what we call as PATM, where we are currently at. Okay, this is what we call by sea level. Okay, this is what we call by sea level. This is the absolute vacuum. Yeah, the pressure. Okay, the pressure. Universe. The pressure of the universe. Universal. VERS. Okay, universe pressure. We don't have any pressure in the space of the universe. Okay, so it's 0, right? It's 0. However, on Earth's surface, we have this pressure. This is what we call as 1 atm. Okay, 1 atm. Normally, calculation wise, right? Calculation wise, when you use like a pressure measuring device, it's not calculating from this point here, fellas, right? It's not calculating this. It's not calculating from this point. Rather, when you use your gauge, it's actually measuring this. Do you know this, fellas? This is what I call by gauge pressure. Okay, this is called by gauge pressure. And the moment you have this, let's say this one is 50, and this one is say 100. This one is say 100 kPa. If this one says 100 kPa, the real pressure is actually 100 kPa plus PATM, right? This is the real pressure. Okay. If you were to calculate the real pressure, you have to measure from down here. And this pressure is what we call by absolute. Okay. The pressure from at the bottom until top is what we call by absolute pressure. Okay. Pressure from here to here is absolute pressure. It's actually 201325 this year. It's not 100 kPa. Okay. However, if you measure using the device, it's going to give you this value. It will give you this value. It's not the real value of pressure. It's actually the gauge pressure. Okay, because it's measuring from the sea level. It's actually measuring from the sea level, right? This is what we call as gauge pressure. Okay, and in this lecture, it says that, right, because the gauge pressure, I think the atmospheric pressure is acting on all the direction, right? All the direction. It's acting on the top, at the side, sideways, at bottom. Okay. So when we are considering all the pressure, all the atmospheric pressure, is going to look like this. It makes the analysis difficult. However, if we neglect, if we remove the atmospheric pressure, the analysis is simpler. It becomes just this with the gauge pressure. Okay, so this is what it says. A common simplification in the application of Newton's law is that we can remove the PATM, right? We're just gonna work with just the gauge pressure, just the gauge pressure. Forget about this. Forget about 0 to 101. Okay, it's common, right? We're just gonna use the gauge pressure. That is 100 kPa. Okay, just the 100 kPa. When we say it's 100 kPa, it's not actually 100 because you have to plus this in order to find out the real pressure. However, we normally use this. So that's why when we talk about when we talk with our colleagues, when we do experiments, we just can be using this value. This is not the real value of pressure, fellas. Okay, just so you know. Right? And then in this analysis, we'd like to assume that because the effect will cancel out. You have pressure on this side, you'll have pressure on the other side. You have pressure on this side, you have pressure on the other side. So it cancels out, okay, in all direction. So that's why, for the sake of calculation of Newton's law, just work with gauge pressure. That's it. In fact, that's exactly what we shall do in our calculation later on. Atmospheric pressure acts in all direction, and thus it can be ignored. Okay. So okay, this is the selection of control volume. Now have a look at this. Would you rather choose control volume A or control volume B? Which one do you think is easier if you were to analyze this faucet, right? This faucet, this pipe, right? If you were to analyze this faucet, would you rather use CA or you use CVA or use CVB? Okay. In the analysis, I think it's easier for us to just use CVB, right? It's easier. Okay, it's easier. Okay, just bear with me. Just few more slides. Just few more slides. Okay, the rest are just equations, right? We're not gonna discuss much about the equation because I think it's pointless, right? I could show you. Okay, just to scare you a little bit, right? Show this. Okay, have a look at this equation, right? Have a look at this. Okay, have a look at that. Have a look at this. Have a look at. Okay, this is just some. Okay, so have a look at this. Have a look at this. Okay, how's all right, have a look at this. Have a look at this. Okay. So we're not going to really talk about the equation. Rather, okay, this bit, we're going to go through very quickly. Right? We're going to go through very quickly. It's pointless for me to explain the equation to you. I would rather show you how to use the equation. Okay, but this one is the general bit. I think just explain a little bit. Okay, so F equals to ma. I think the equation of a momentum equation, the linear momentum equation, F equals to ma. I think we can agree on that. And then I think it's been shown later on, earlier on, that you can expand the A into dv over dt. So m multiplied with the v, okay, is the momentum, right? So that is why this equation, the Newton's second law equation, m equals to ma, is also said to have the rate of change, because the dt here, the rate of change of momentum. Okay. Density may change from point. Okay. F dt. Okay, you can change this. M because you know m is the dv. Okay, you can express this in the form of rho dv, okay, which is the volume. Okay, this is the velocity. Okay, v here is the volume. All right. Okay, you can change that accordingly depending on the situation. Okay, so right, you can read this. Okay, so the okay, in general, you can write this equation down. Okay, in general, you can write this equation down. The sum time. Okay, this is okay, explanatory. Okay, dmv. Okay, mv is the force, right? Okay, mv is the force over dt equals to the. All right. Okay, the body and the surface. Remember this. Okay, if you go back like several slide. Okay, the force. This is the force. The F equals to ma. The force. Okay, over dt. Yeah. Okay, the force, the control volume, on body, and then on the surface, right? On the surface. That's why if you were to rewrite this, okay, the change of force, okay, the dv, okay, this is the control volume of the body, and this is on the surface, right? The body and the surface, the sum of all the phase. Okay, this explains. Yeah, the sum of all the external forces acting on the cv is the time rate, the change for the cv, and then the net flow. Okay, everything for the surface. So for the fixed CV, okay, for a fixed CV that's not movable, that's not deforming. Okay, for fixed CV, the force is given by this equation. Okay, for the body as well as for the surface, right? Don't remember. Okay, don't worry about it. Okay, this is just how they play around with the equation, right? You can change this equation, the one we get earlier. Okay, this is the equation. We can change this into this. By replacing b equals to mv and small b equals to v. Okay, you can rewrite in this way. Okay, which is okay, not really a big issue there. Okay, so you have this equation again, right? The one that we discussed earlier, F equals to the body, the surface. Okay, the body and the surface, rho V and body and surface, right? This is one of the example. I think I would rather show you an example, right? Don't worry about this. Okay, steady flow, yeah, steady flow. Okay, I think I show you this, right? Do you still remember when, yeah, when you have momentum on the right hand side, then you have a momentum on the left hand side. Okay, it cancels out, right? It cancels out, right? So that is what happening here. Okay, if you notice, this is just the body. Okay, this is just the surface. The body is gone. From this equation, this bit is gone. Okay, this bit is gone. Only left this one. Okay, for special for a steady flow devices, this bit is gone. Okay, this term of the equation is gone. We're just leaving as this. Okay, just leaving as this, right? Remember that. Okay, special case. Okay, why? Because of the equality of the momentum. That is the third law of Newton. Okay, this is the situation for third law of Newton. When you provide momentum to one body, another force is acting on the opposite side. Okay, that is Newton's third body. Okay, you have water here, okay, being the which carries along the momentum, and then you have another momentum on the other side. Okay, so that is why in the calculation for the steady flow devices, the one on the body, on the control volume, will be neglected. Okay, we're going to cancel out the CV, which remains the CS, but CS is the one that's difficult. All right, okay. Okay, then you have mass flow rate. Okay, how do you calculate mass flow rate for circular? Okay, I think you know this. Mass flow rate equals to rho AV. And then momentum flow rate. Okay, right. You can also rewrite this as MV. Okay, because all right. Okay, MV average. Right. In a typical problem, the control volume may contain many inlets. Okay, you have many inlets and then outlets. Okay, that is not important. Right. Example of inlet in which uniform flow approximation can be used. Okay, there is like an approximation used for uniform flow, and this is the situation where it's applicable. Okay, you have the well-rounded entrance of a pipe. Okay, where the entrance of a wind tunnel, and then a slice through a free jet through a nozzle. Okay, when you have this kind of situation, we can assume uniform flow approximation. All right. Okay. This bit is quite important. Okay, this bit is quite important. In fact, this is the equation. This is the equation that you will use in the calculation palace, right? You can, I'm not asking you to forget about the rest of the equation, but then again, you have to know where it's coming from. But this is the equation that we are interested in as far as your calculation is concerned. Okay, this is the equation, right? This is the equation that we shall use. Momentum flux, the beta here, okay, the B here, we can replace this, the surface here, okay, as the B. Okay, the velocity across most inlet and outlet is not uniform, right? The velocity is not uniform. Thus, okay, the control surface integral, okay, we can convert it into a algebraic form using a dimensionless correction factor called momentum flux correction factor. Okay, you can expand the surface here, okay, with regards to the entry of the flow minus inlet of the flow. Okay, this is flow at the exit, this is flow at the inlet. Okay, so when you have this, you can expand this by using the correction factor as beta here. The correction factor is given. Okay, it depends on what type of flow that you're dealing with. The B here is for turbulent is 1, for lamina is I think it's not it's not 1, right? There'll be a different value. I think the value for the B will be given, okay, for any calculation. You don't have to worry. Okay, momentum flux across an inlet or exit. Okay, this is how it is. All right, after you differentiate this with respect to A, this is what you are going to get. Okay, this is what you're going to get. Okay, all right. Okay, so this is the beta. This is how you calculate the beta. Okay, given by this equation. All right. But I think most of the time we will give you this beta value. Okay, but just so you know, this will be the equation that is of specific concern in our calculation. Okay, so this is an example for laminar flow. Okay, this is the correction factor. How you find correction factor for laminar flow, which is okay, this is the velocity profile for laminar flow. I think the value for the correction factor is quite. It's not the same as 1. Yeah? It's not the same as 1. Okay, that's what. Okay, it is wise to include to be in all momentum control of volume problems. Okay, that's understandable. May have it. Okay, for turbulent, this the correction factor. That's why they put as 1, because it's not that significant. However, for laminar, yes, this B value is very significant, so you have to bear in mind. Okay, so this is the case for laminar, and then for steady flow, okay, like I told you, for steady flow, the V cancel out. Okay, for okay, where is it? Okay, for steady flow, like I told you, this one cancels out, which leaves us this. Now, the moment you expand this, you get this, right? So it means that for steady flow, okay, for steady flow, this is the equation to use, right? This is the equation to use. Just 2 more slides. Okay. Just have a look at this equation. This is the one that we use for steady flow. And then this is the one that we use for steady flow with one inlet and one outlet. Okay, if you have one inlet, one outlet, this is the equation to use, right? And then when you have no external forces, this will be the equation to use. Okay, this will be equation to use. And that sums up this chapter. Okay, that sums up this chapter. Right. I know. Okay. By just looking at the lecture notes, I don't think you get anything out of it. To be honest, you get more confused as I move along. Right. So that is why I think next bit is for us to use try out some exercises. Okay, is to try out some exercises. I think it's gonna get easier. Okay, it's just gonna get easier if we try on these exercises. So please bear with me. Okay, just bear with me because um if the question is going to come out, this is basically how we are going to do the analysis. Okay, how we're going to do the analysis, right? Do you want to take 5, fellas? Okay, take 5. Will I take 5?
Yes, sir.
Okay, just take 5. Eh? Okay, try to digest. I uploaded the slide in Elip. Okay, okay, I'm showing my screen near here. I think you can see this. Okay, this okay, a chapter. Um, you can upload this. Okay, you can download this. I can have a look at the slide. Right, you can have a look at the slide. Okay, so take 5, please. And after at 1 p.m. we're gonna be doing some exercise. Right, we're gonna be doing some exercise. Okay, in the meantime, right before that and after that, I'm going to give you a question. I'm going to give you a question. Okay, so please take your attendance in the meantime.